And we are ready to start. Welcome everybody to the second class of the Coming Up to Speed summer course. We have somebody new. Troy, do you want to introduce yourself? And by the way, can I ask you to move all the way in there? If it's not too inconvenient, because I have one microphone for the room. I'm solving that right now, but if you can be mindful that that's the only thing that is standing between you and people not hearing you.
I'm Troy. I'm an undergraduate at LSU. I'm doing research at application software.
Thank you. I see some new people in Zoom. Daniela, you already introduced yourself. Gabby as well. So a reminder to be nice to each other and to yourself. That is very important. Showing again, this is a list of resources that we're using. If you follow the link to the folder, now it has stuff. Before it didn't have stuff. I have put in here a folder with previous subject exams. For those of you that are very interested in studying for the classical and quantum exams, these are previous versions of those exams that you can find in there. I will be putting the materials of the lectures in the folder lectures. And yesterday I was actually able to edit the video from the first class directly and put it in YouTube. Now that is there, so you can rewatch it if you think that it's as good as Lord of the Rings and you have to rewatch the same thing 10 times as I do. Or if you were not present here and you have to watch it, you watch it there. But as life gets complicated, there will be times in where I don't have the chance to make the full edit in time so that you can watch it before the next class. When that happens, I will put the raw recordings in that folder that says raw recordings. It will not be edited, but you can listen to it and it will help. This is a summary of the lecture that we had last Monday. I gave an introduction and everybody introduced each other as well. We talk about why this course is important, and I'm going to repeat it because it's very important that this message gets through. The fact that there's some details and concepts and things that you might not know as much as you might want to start your grad school doesn't mean that you're not prepared or qualified or able to do this. You have done many adventures in your undergrad, but that's why I'm here. I'm going to help you prepare for the specific adventures that we're going to be tackling in grad school. So that's the analogy with the beautiful pictures and the ship sailing across the sea. We talk about calculus. We went over the list of inventions before the 17th century when we didn't have access to calculus, and the list of inventions after. And we realized that there is a big difference. They're more complicated. It's a more complicated story. You have penicillin and the ability to have cities in where you have millions of people. Calculus was a big part of that revolution. And we talk about derivatives and integrals. In particular, on the derivatives, I forgot. That's the thing that I was forgetting. I forgot to bring the cylinder. I will do that during the 4-minute break that we have. For the derivatives, we talk about why they're useful. In my opinion, the most useful part is they allow you to do optimization of functions, especially in multiple variables, that at some point we will touch on that. And they allow you to write differential equations, which is a way of describing how a system behaves locally in time, space, parameters, however you want to think about it. And we did play the game of optimization with hot and cold, and Cooper was able to get himself a free ice cream. That is still on you. I need to go to the dairy store to buy you the actual coupon. And we talk about integrals, and the main point of integrals, I should make this more of a dialogue instead of a monologue. Anybody remembers what integrals in a nutshell are useful for beyond calculating areas under curves?
Summing up all the little contributions of something and calculating a full contribution.
Excellent. Areas is one specific example of that. But what you describe is extremely powerful. It allows you to break something in many, many tiny pieces and add all the contributions. And the example that we look at was a charged potato and trying to calculate the electric or the electric field or the electric potential of the charged potato. So very happy. Thank you for remembering that. We did the demonstration that failed because I didn't bring the correct size of the cylinder and I forgot to bring the cylinder again. I will do that later during this lecture. This is a link to the video that you can see in case you have not had the chance to look at that. Also, you might have noticed that we are going to cover the equivalent of 3 years of undergrad in 2 months. I had one class on derivatives and integrals. I'm going to have one and a half class on differential equations. I'm going to have probably 2 classes on linear algebra. Obviously, there is not enough time to go over many of these details. That's not the idea. The idea I want to give you intuitive pictures of how to connect with these subjects. But you may need more. So remember that in the GitHub repository, we have guides that go step by step in many of these things, in much more details that I can do during the lecture. So go and check it out. This was written by Josh Wiley, and it guides you through very nice ways of visualizing derivatives and integrals and actually implemented them in code. So we were talking about the playground, and Daniel was mentioning, so I'm going to try again with names. Daniel, Cooper. No, can you remind me your name? Allison. Okay, sorry. And Troy. If I forget your name, I'm terrible. And in Zoom, I think we have Gabby, Tess. Lauren, are you able to? I see some people that have not introduced themselves. Protoy, do you want to unmute yourself and introduce yourself if you have access to a microphone?
Yeah, sure. Thank you very much. Hi, my name is Protoy Samir. I'm from Bangladesh originally. I completed my master's from New York. So I've already been in the US for 4 years. Right now I'm back in Bangladesh. I'm trying to reconnect. I'm trying to connect with my physics community at Michigan State. Couldn't attend my first lecture or our first lecture on Monday, but right now joining in my second class. Hope to be present in the following lectures, that is.
Fantastic. Very happy. Nicolas, can you unmute yourself and introduce yourself if you have the chance?
Yeah, can everyone hear me?
Mm-hmm. I can hear you.
My name's Nick. I actually did my undergrad at MSU. I work in AFRIB with Xing Wu, and I decided to come back for my grad school. So I'm the first year PhD student, or I'm an incoming PhD student, and I think we've met a few times, Pablo, but only sort of passingly. So I think I have met you before this class, actually.
That's very likely, and I'm sorry, my memory is not what it used to be, or I'm not sure because I don't remember, but I usually don't remember things. So I'm sorry, Nicola. But nice to meet you virtually. I'm very glad that you like it so much that you're coming back.
Yeah, and I'm nice to meet everyone else as well. So it's not just my introduction to you. Obviously, it's all good that you don't remember me.
Excellent. Very happy. Sarah, have you introduced yourself before? I don't think so.
No, I have not.
Please go ahead.
Hi, everyone. My name is Sarah. I'm an incoming PhD student. I just finished up my undergrad at Temple University in Philadelphia with a double major in math and physics.
Nice. Very good. Well, some friends, thank you for joining us. I think Lauren is still struggling with the microphone. We're going to continue, and at some point, she will unmute herself. I fully expect, I know people that told me that they were going to be here, and for reasons, life is complicated, they have not been able to join us. So as the lectures progress, I expect that we'll have more and more friends. Playground, anybody tried any of these things and wants to comment? Daniel said that you were able to do every one of them except the podcast. Do you want to say anything about any of them?
Sure.
So for example, for the first one, did your derivatives approximate the derivative, what you expect?
Yeah, they were pretty close.
Nice. So I encourage you you can comment on the forum and say, this is what I tried. You can put a screenshot of the pictures. I forgot about doing this, but I will make a branch of the GitHub repository where you can upload your playgrounds, the parts that have to do with coding. That can serve for future students, and I can give you feedback. Anybody else tried anything that wants to comment from the room? Please.
I did the third one. Just use Riemann sums to find the circle. It was pretty close.
Good. Yeah. To the formula. We still don't know the actual volume. We'll have to wait for the water. But yeah, very good. I'm very happy. Excellent. Make sure to listen to the podcast. I will argue that among everything that I'm sharing with you right now, that one is probably the most important one. And later I'm going to start keeping track every week of the playgrounds that you complete so that I can give you the certificate at the end if you like collecting those things. So don't forget about it. Okay, with this we can start lecture 2. So I'm going to start sharing the screen of my tablet. We're going to talk about Taylor series. We're going to motivate why on earth anybody will be interested in doing something like that. We're going to have a fun activity, then we're going to have our break, and then we're going to talk about differential equations. I will share with you how I view differential equations as the rules of a game. We're going to talk about the math dojo. That is the dojo in where the further you advance in levels in the dojo, the more complicated problems you're solving. And I'm going to talk about 2 differential equations that I really hope that you commit to memory. And then we're going to have a fun activity that is hiding behind the screen. I don't know how that one is going to work out. We're going to try. So let's start with Taylor series. And my first question to everyone, what the heck is this? Any ideas? What comes to mind? Probably you have seen it. Probably you remember something. Maybe you already know everything that there is to know about Taylor series. Maybe you don't. I want to hear what is in your head when I mention this. Some people. Let's start with you. Anybody wants to mute and comment something?
Yeah, Taylor series helps us to approximate functions up to nth orders.
Approximate functions. I like that. You mentioned something. You mentioned an order. I am very messy. Everything in my house is in disorder. What is disorder?
It's the exponent of or the variable of the function.
Okay. So I hear the word exponent. Thank you. Room people, anybody have other things in mind? What else comes to mind when somebody mentions Taylor series?
Expanding a function to
Expand.
find the limits.
Expanding. You say the word limit. By the way, this is something that I just started doing in this iteration of the course. I like writing what comes to mind to all of you. That also helps me build a mental map of what are the connections. I like the word expanding. What else? Any other thoughts from anybody now? Okay, now you and I are going to play a game. I am going to grab a function. We're going to grab the sine function that you all know and love, sine of x. This friend looks like this. Very important that I nailed the behavior near 0. All right, I did my best. This function looks like this. Yeah? You have calculators, you have computers. So in principle, you can compute this function anywhere. But if I were to ask you for $1 million in cash, what is your best estimate that you can think of? Obviously, if you already know what Taylor series are, what I'm asking is very trivial. But try to forget. Try to forget for a second. Imagine that we are in a desert island. We don't know physics. We don't know math. We are kind of inventing this. And I ask you for $1 million and I don't know where I got them in the island. What do you think is the best guess you can give me, numerical value, for the value of this function at 0.01? If you had to just say a number, what would be the best guess that you can give?
0.
Excellent. I love it. 0 is a much better guess than 35. Particularly the sine function is between -1 and 1. But the best guess that you can give me to the value of this function at a small number, you have no idea. The actual value of this thing is very complicated to estimate it completely. But you do know the value of the function completely precisely, close enough. This close enough is this friend. So you do know that the value of the function around that is 0. I'm very glad that you said 0 and you didn't say something more complicated.
35.
Sorry?
35.
Well, that yes, that will be even worse. But yes. Again, some people, if there is something that I say that doesn't make sense, you need to interrupt me. So yes, this is a fantastic first guess for the value of the function. If I were to tell you, I love it, good job, but I want something more. Can you be more precise than 0? What will be your next approximation, your next order approximation? Somebody else that is not Alice.
Pretty close to linear at that point.
So Cooper is saying the following. You zoom in, and once you zoom in, you realize that, well, that I don't know how to draw a straight line, and I draw many, but you also realize that this function, I'm going to put it, let's put it in orange. This blue function, you can really approximate that by a straight line. Yep. You already understood 90% of what Taylor series are. Is you want to understand the value of a function at a point that you do not know. If you already know it, then this is silly because you already had the answer. But you know something about the function in a neighborhood, in a place that is close enough. And you're going to use that information to make a more educated guess. That is what relates to the order that we were talking about. So numerically, help me. If I want to know the value of the function at 0.01, what is that extra addition that I can do to improve my numerical values even further? Neither Allison or Cooper. Someone else. Some people. I want input from you. What do you think I could do?
0.01.
So you say 0.01, which is correct, but how did you come up with that number? Can you guide me through the process so I can understand how you got that value? I'm going to put it here in, let's put it in black. You said,
I would say that orange line just kind of looks like y equals x.
Excellent. So this orange line, so let's write it. Let's be a little bit more general for a second, because you're absolutely right, but I want to give you a method to calculating these things later. This is a straight line, right? So I will model this as mx plus b with some slope and some intercept. Yeah? Those are the two parameters that will characterize this straight line. How much should b be for this case? 0. My straight line is passing through 0, so no b. So it's just mx. I need a way of estimating how much is the slope of this straight line. How much is the rate of change between y and x for this orange straight line? Who muted? Because I cannot see your name when.
Oh, it was me, Sarah.
Sarah. Okay, sorry. Now my tasks gets more complicated. I have to start memorizing people's by voice. Sarah, any idea? You estimated it correctly. You said that it was 1. But how could we convince ourselves that a good guess for this slope is 1? Do you have any ideas?
Well, my idea would be to look at the derivative of the function.
Oh, fantastic. Yeah, everybody sees that? What are we trying to do? We're trying to approximate the blue curve. And we're saying, very close to 0, the blue curve should look like a straight line. Well, very close to 0, that sounds like taking a limit. That sounds like looking at very small changes in x and how much that impacts changes in y. That is exactly what a derivative is. So what I need, and I'm going to say something that is wrong, but I'm going to say it anyways and see if somebody catches me. What I need is to estimate the value of the derivative of my function here. That will tell me the value of my straight line. So I need to calculate if my function was f of x equals sine of x. I will have to calculate f prime at 0.01. And that will give me that slope. What is the problem on this? There's many problems.
Cosine?
Sorry?
Derivative is cosine?
The derivative of sine is cosine, perfect. So I have to calculate cosine of 0.01, and that will give me that value. How much is cosine of 0.01? It's about 1, but can you do better than that? Or what is the problem in here? Try to speak a little bit louder because of microphone, but yes, that's exactly true. I have the exact same issue, that this is another function that is complicated. So how can I circumvent this issue? What is the solution to this dichotomy that we have? What can I do? One way is true, is I just cover my eyes and approximate cosine of 0.01 by cosine of, by saying that it's close to 0. But can I do something a bit more rigorous? Why am I evaluating the derivative there? I don't know the functions there. But I know the function at 0, and I know how to calculate every derivative at 0. Because the derivative of sine is cosine evaluated at 0, that is exactly 1. If I will see later that I want to improve that, taking more derivatives, that will be minus sine at 0, that is also trivial. So basically, you have an infinite amount of information around 0 because you can calculate the value of the function, the value of all the derivatives there, and that's what you're going to use to kind of build a ladder to give a better and a better approximation in there. So when we were asking this question, the error was to try to approximate to calculate the derivative at this point, which is what I do not know, but rather say, no, well, don't erase the whole thing. Calculate the derivative here, and now is f prime at 0. And that is cosine of 0, which is 1. Technically, if you wanted to do this numerically perfect, the value of the derivative, you should calculate it kind of halfway through. Doesn't matter, those are details. We're discussing Taylor series, not computational approaches. Anyways, who is the slope then? This slope is going to be f prime evaluated at the location where you're expanding it. So a better guess of my sine function is this 0.01. So look at how I'm going to write this. I'm going to write this. This is 0 plus delta x, where delta x is 0.01. So 0 plus delta x times f prime evaluated at 0. Make sense? This is the value of the function where we were. I calculate my derivative. I multiply by the small amount of change that I'm after. This basically, if you think of what a derivative is this is delta y over delta x. Small change in y with respect to small change in x. I am interested in approximating a small change in y. Well, that is just f prime times delta x. Make sense? All right. How can I improve this even further? Because this is a very good number. This entire thing ends up being 0.01, which, by the way, if you have ever solved the pendulum equation in physics, usually you end up making the approximation sine of theta equals theta. This is where it comes from. How can I improve this even further?
Our top curve is kind of like a parabola. The second derivative is.
So if you see so let's try to look at this. Okay, this is getting a bit cramped. I'm going to remake my figure here. This is your sine function. And this is your approximation. Oh boy. Can I cannot do something better than that? Okay. There we go. All right. That is my approximation. You see that eventually my approximation starts failing. I will be very happy if I could push this orange line a bit downwards. I will be very happy if I was able to push this orange line a bit upwards. If you use a parabola, the problem with the parabola is that it will, if you use it positively, it will push on both sides in the same direction. That will not improve my approximation. So I need something that on the right-hand side smacks it down, on the left-hand side makes it go up, and close to 0 doesn't do anything because it's already really good. What could that be? That is not a parabola. What function do you know that it looks like that? A cubic function, if I were to think of a cubic, if I plot just a cubic function, it looks like this. This will have not the desired effect, because if I add it, it will push on the right, positive, and it will push on the negatives to be more negative. But if I multiply by a minus, and I get exactly what I want. is something that close to 0 doesn't do anything. And away from 0 is that extra correction term. This is a series. This is something that is an improvable expansion. The more terms you put in this thing, the more close your function is going to be, your approximation is going to be to the true function. Any questions so far? Does this make sense? Is it helping with the previous thoughts that you had? There is a formula for the Taylor series that you can memorize. I usually prefer to at least intuitively think of the first terms. If I say that I'm trying to approximate a function x, a function f of x around a point A, let's try to derive this together. What is the best approximation that I can give you to the value of the function around A? Alison, you got this one because you did it very well last time. What would be the value here? What is the best guess for the value
0.
of the function? No.
Okay, I didn't hear the question.
That's
Said
it.
I got it right last time.
But excellent.
A.
No, not A. It's not AI.
Oh.
Give it a third try.
Can you say the question again?
Yes, of course. What is your best guess for the numerical value of the function f of x when x is around A?
Oh, f of A.
Very good. This is my first term. This is the first crudest guess that you can give to the function. Yep. Give me a correction. So if you define, let's say, delta x is equal to x minus A, how far away x is from A, what should be the next correction?
X minus A.
So delta x, that is how much I move a little bit in x. I multiply that by what to obtain the correction in y, which is what I want.
F prime A.
Excellent. F prime evaluated at A. This is important because some people get confused. This is a number. This is not a function. Well, it's a function evaluated at a location. What is the next correction? Well, it's going to be something that takes into account a higher terms in my difference. So it's going to be something proportional to the delta x squared. That is exponents or the order that we were talking about before. What should be the coefficient of proportionality? Now, when you talk about the linear term, it's very easy to derive it. In this one, if you just do pattern matching, has to be something that relates to the second derivative of f, evaluated at A. That tells you about the curvature. Annoyingly, there is a 2 factorial that you have to just remember to divide by. The reason why the 2 factorial appears is because you're kind of trying to match this into a series of a polynomial. And whenever you make derivatives of x squared, you're going to get a 2 that is going to come down. That number is important numerically, but it's the less important part of the whole concept. If you were to tell me what is the next term on this series, what will that be?
Delta x.
So reasoning in this way, it has to be something that is proportional to delta x cubed, yes? Has to be a term that knows about the function, right? Otherwise, this will be a Taylor expansion of some random stuff. So what term will you put that relates to the function?
Third derivative.
The third derivative, yes. Evaluated where?
At A.
Ah, fantastic. And then there is the annoying number that you have to put. You look at the previous steps and you realize, but of course, 3 factorial. And you see you can derive, the rest is just a series. But that's what every one of these terms mean. Does that make sense? All right, we're going to do a practical exercise. Before we do the practical exercise, any questions, any clarifications, any other comments? Another way that I like to think of Taylor series, if it's useful for you to visualize this, is think how an ant will look at your function. So if you're trying to expand a function near this point, is basically you zoom in and you put a tiny ant. This is my best interpretation of an ant. And for the ant, the curve looks basically flat. But once it starts moving, it will curve a little bit. This is kind of the same thing that happens with flat earthers. They just stop at the first term in the expansion of the curvature of the earth. So for them, they don't see that the thing, nobody told them to go to delta x squared. Okay, so the practical example that I want to solve, I hope that we're going to have time for this, is this one. So we talk about what they are. What could be the usefulness of a Taylor series? When is this useful in an engineering and scientific way? Can anybody tell me? Some people, I haven't heard you for a while. Do you want to mute yourself and tell me what could be the use of such a thing?
It could be useful to approximate functions around the periphery of a desired location.
Yeah. So to numerically be able to say anything, to compute things, every time that you have something like a sine, cosine, exponentials, or even more crazy functions that we will talk about later, if you didn't have a computer, you don't have a way of approximating this. Even if you have a computer, whenever you have a very complicated nonlinear differential equation, trying to solve it for real is extremely expensive. If you can make some approximations here and there, that you substitute some of your operators that are very complicated functions by functions that are polynomials, your life is going to be much easier. So basically, I want to think of this as an approximation tool. That I want you to realize the power of this approximation tool and think it as a tool. It's something that you're going to have in your bag. I don't know if you're all of you are old enough to be in this situation, but I already have in my own place, the place that I live, I own a box with tools. I have a hammer and I have a, I don't even know how to say that in English, the thing that you use to grab things.
Pliers?
Maybe. Alicate is in Spanish. I have a screwdriver. I have a bunch of stuff.
Pliers.
Wires?
Pliers?
Pliers? Okay, pliers. Thank you.
They have like rubber handles.
Yeah, exactly. That when your teeth are hurting very much and you have to take it out, that's what you use. Yes, exactly. So I have that box with tools in my house, and I want you to see it as a tool. I don't want you to see it as one thing that you have to memorize, and all of a sudden you're going to be in quantum mechanics and your professor is going to be, quickly, what is a Taylor series of the sine function? And if you don't know that by memory, you're screwed. No, it's a tool. It will be useful for some things. It will not be useful for other things. Try to see it that way. That's one of the failures that I see in our education system, in where we give you a bunch of information, but never give you the context on why this is going to be useful. So you treat it as a bunch of stuff that you just have to carry around. It's a whole, that will take way longer than this. So I want you to guide me in solving this problem numerically. I'm going to try to speak very little. I am after finding the numerical value of x that solves this equation. The root of this equation. I can do it numerically with a computer, but I don't want to. What can I do to find a number of x that solves this equation? Tell me, people. I'm all ears.
Taylor series.
I cannot hear you.
You do a Taylor series.
A Taylor series, fantastic. Let's expand x squared. So x squared around 0, is that the one that you think? Oh, by the way, I am assuming that the solution to this problem is around 0. Should I expand x squared? And what will I get if I expand a polynomial?
Polynomial.
The same polynomial? You better have the same polynomial or you did something wrong. So who do I expand in Taylor?
The exponential.
And why?
Because you can't like solve for x with having x squared in that.
I have no idea how to find the value of x by hand if I have an exponential in the middle of things. So, okay, let's follow you. Cooper, what is a good Taylor series of this friend? Around 0. Can you guide me slower so that this helps future people?
Yeah, first we'll find the value of e to the 3x around 0.
And that is?
At 0, which is just 1.
Excellent.
Adds that the derivative of that at 0 times.
How much is the derivative of e to the 3x? Is 3 e to the 3x evaluated at 0.
Right.
So this is 3 times e to the 3x, all of which is evaluated at x equals 0, times delta x, which in this case, I'm expanding x around 0, so this is just x. And we're going to stop there. So this is equal to 1 plus 3x. Yeah? So I substitute this in here and I get x squared minus 1 minus 3x plus 2 equals 0. So this is x squared minus 3x plus 1 equals 0. Ah, and now I can solve. The solutions to this is going to be 3 plus minus the square root of 9 minus 4, so 5. Square root of 5, that is a pretty number, divided by 2. Now, is this really the root of this equation?
It's an approximation.
Excellent, it's an approximation. So if I grab this number and I plug it in the equation numerically and evaluate everything numerically, by the equation, I mean the actual equation that we're trying to solve, I will not get 0 on the other hand. I will get a very small number. Suppose that I want to go further and get better at that number. What do? So it will be, I will have to add something here that will be proportional to x squared with some constants, and then I solve again. Yep. If I go one step further, I will have a third degree polynomial, and I don't know about you, but I don't remember the cubic roots expression for a third degree polynomial. But that's the spirit of this thing. Makes sense for everybody. Any questions so far? I congratulate you. This is probably one of the first times that you're consciously using Taylor series to actually solve a numerical problem, at least following the steps onward. Okay, so the next thing that I have for you is our activity. So this is your activity. For the next 5 minutes, you are going to sit down and are going to try to find how the Taylor series, or the terms, the first 2 important terms on the Taylor series of these functions look like. Now, this is a bit tricky, and while I was preparing this, I realized that might be even a bit confusing. But here's the idea. The way that I made this Taylor series is such that I already took into account the value of the function at that location. So sine, you're expanding it around 0. E to the minus 2x, you're expanding it around 0. And 5 plus 1 over 1 minus x, you're expanding it around 2. And you see that all these functions, for example, this function f at 0 is 0. This function e at 0 is 0, because I already took into account that offset. So whenever you're expanding sine at 0 is 0, but whenever you're expanding the exponential, that 1 is already taken into account. The same for this one. So basically, I'm asking you, after you take into account the constant value, what are the 2 orange curves that I have to literally just add on top of that constant value to get the behavior of the function around the location that I'm expanding? Is 212. I will resume here at 217. I recommend we have 4 people in the room, that you pair in groups of 2. And soon, folks, you just have a hearted discussion, and I will be back. Okay. We're ready to come back? Some people, can you hear me?
Yeah, we can hear you.
Were you able to have a good discussion?
Yeah.
Okay. So I'm going to start with you then. Tell me, what are your thoughts on the first one?
I mean, we just said the first one is just like the example that we did. So it should be H and F as the contributions. And yeah, and that makes sense because the Taylor series. Oh, sorry, go ahead.
No. Go ahead. I'm listening.
Yeah, the Taylor series for like sine is just the odd terms.
Yep.
So
yep. Excellent. Perfect. So if you I want to drive the point home that you can try to zoom in on this thing and see it, and it's basically a straight line that passes through 0. So I 100% agree with you. Should be H. You had 2 other straight lines, but none of them pass through 0 and at the same time have a positive slope. So that discards them. And then the extra correction term, exactly as you're saying, has to be something that looks odd, as in even odd, and curves in the way that it curves this for them to correct. And if you were to do actually the Taylor series expanding in derivatives, you will find out that sine doesn't have an even term, it just has odd terms. And the next one is x cubed. Excellent, thank you. Okay, somebody in the room, what do you think about the exponential? What should be the first term?
We were thinking that if you take the first derivative of e to the minus 2x and evaluate it 0, end up with 2. So the first term, and then the delta x is just x. So you end up with something that is linear with the slope of negative. The first correction term, which looks like
that looks like e, right? It even matches. If you look at the 2 in here, it's around -4, so it even matches the slope because I did these things very carefully. That makes sense? Okay, what about the next term for the exponential? What do you think? Can you speak a bit louder?
Right. Yes, we were thinking I because.
Okay.
Well, so yeah, so it's going to be a quadratic term, x squared, in the Taylor series, and also the other two have their x-intercepts at 2 rather than 0. Centered at 0, function calculated at 0.
I am happy with all those arguments. The fact that it's a parabola or something doesn't have to be a parabola, but it has to be something that, well, sorry, of course it has to be a parabola. We know it by the Taylor series. So even if you didn't know that, it has to be something that corrects the straight line by making it curve up to the right and making it curve up to the left as well. So that's why I'm showing you a different way of reasoning this through. That's why the next correction has to look like that. Has to be like x squared. Makes sense? Everybody sees that. Yeah. So yeah, well, the next one, you can do it by inspections, just by seeing the things that you are left with. But I did want to put an example in where I'm not expanding around 0. So your job really is to look at this function, go there and see how an ant will see it there. And an ant will see there that after you take into account the intercept, or yeah, the intercept basically, that you have a function whose correction at 2 is equal to 0. That's why the straight line intercepts 0. The straight line will look like x minus 2, all of that multiplied by the appropriate derivative, which in this case ends up being 1. And then if you apply the same reasoning, well, you have a straight line in here. You have to correct it to lower it to the right and lower it to the left. You're left with a parabola that is a sad parabola. Make sense? Any comments? Some people, any questions? Anything else you want to add? Okay, so now for real, we're having the 4-minute break. It is 2:22. I will see you back at 2:26 and we start differential equations. Okay, we're ready to continue. So, before we actually go and do differential equations, I realize that I owe you this. How am I going to do this? Does this work without breaking the thing? Okay. That I owe you the water activity. And here I have my graduated cylinder. You can see, let's see, is around, I have no idea why this goes from top to bottom, but these ones go the way they will expect. I have 100 milliliters of water, and we're going to add this thingy. Try not to spill any. And I read almost 50 extra milliliters. Let's see if I can estimate that better. Maybe like 40. That's my guess. I don't know. This is as even as I can hold this thing. Almost 50 milliliters extra. So you can now compare to the volume that you obtain. You can tell us later, Alison, and we can continue. All right. Okay, let's talk about differential equations as the rules of the game. What game? Differential equations. Oh, what happened here? So you know what I'm going to do. I'm going to ask you, what comes to your mind when we think about differential equations? What comes to mind? Heat. Yeah, solving differential equations with a computer produces a lot of heat. I agree. What else? So I'm going to put it here, heat. Probably you're thinking of the heat equation. What else? Wave equation. I hear springs. What else?
Circuits.
Circuits. I do remember that too. Circuits. What else?
Derivatives.
It's in the name, so it better be somewhere. Derivatives. One more comes to mind, if anything. If I had to answer this question, I would put manifolds. But that has to do, that is kind of cheating. That has to do with my research. If you're interested, I can tell you more later. But you see that with the exception of derivatives, everything that was listed here is physical phenomena, systems. Systems that as engineers / scientists that we're trying to describe. We're trying to understand how the system behaves, evolves, changes with respect to certain configurations. So the word change, derivatives, that is kind of embedded in there. The way that I like to think of differential equations is a set of rules that you decide. So there is the branch, the mathematical branch of what differential equations means, and then there is a part that has to do with physics and engineering and how we make this something useful. In the pure mathematical sense, I still treat this as a game. You're writing the rules of a game, and you're going to propagate that game in X, in time, in whatever. For example, when you write your differential equation as, and we're going to play with this in the final activity of today. When you write a differential equation that tells you f prime of x is equal to 3 times f of x, and you say, my initial condition is f of x at 0 equals 1, you're inviting me to play a game with you. You're inviting me to make a graph. Maybe I'm the only one that comes uninvited to these type of things. But you're inviting me to make a graph and say, okay, I got you, buddy. This is my initial condition. So at 0, my value is 1. And I'm going to use this to update the values and start propagating a solution. This is going to tell me the derivative at 0. We're going to go in detail on this later. But the derivative at 0 is going to be 3. So it looks like a slope that is using this Taylor series idea that we had. And I'm going to move here using a derivative 3, and I got this value. Now I calculate the new derivative. So it's like a dance. We're basically dancing. You're telling me what are the rules of the game that we're going to dance to, and I'm going to start solving this, and I'm going to end up with a curve. That is a mathematical side. The physics side, why this thing ends up turning or appearing in so many systems, so many descriptions of systems, is because as humans, sorry, there is a distraction coming in. I'm very excited to see what is coming down the hallway that is making that much noise. What was it? Do you see it?
I did not. It's metal. I saw wheels in metal. I don't know what's up with
Yeah. The reason why it appears a lot is because as humans, we are not very good at describing a system by just saying, and this is the time evolution of my system, period. But basically solve it. but we are very good at describing, at trying to come up with models on how the system changes a little bit in time, how it goes from this configuration that is in right now to the next configuration, kind of like a Taylor series. You're very good at writing that. Once you do that, you end up with a differential equation to model your system. And now you have to go and talk with your mathematician friends to be like, I have no idea how to solve this. Please help. They help you, you get a solution, you get something that describes springs, circuits, heat, wave, etc., describes the phenomena, and you feel very proud and very happy about yourself because you're actually doing physics and engineering. Makes sense so far? All right, that's where differential equations are going to appear. Now, before we continue, I want to talk to you about something that I call the math dojo. And I'm thinking dojo as, you know, karate, kung fu, these people where you get better at a specific technique, and then you get these belts that tell you which level are you. So I make the math dojo as something that has levels of difficulties of problems. And the further down you go on this ladder, the harder things become. Level 1, this is completely made up, by the way. It's just my way of illustrating this. For me, level 1 of the math dojo is single variable equations. Kind of what we were solving before. If you have something that looks like x squared minus 2x plus 1 equals 0, that is a level 1 problem in the math dojo. Even if it has the exponential, that might complicate things, but still I'm going to characterize it as level 1. Make sense so far? Again, this is made up and it's not complete. You can have level 2 problems being way more complicated at level 4 if you complicate your things enough. So this is, don't take this as a religion, take it more as a guidance. Level 2, I will argue, that are integrals. So when you write something like the integral of 1 over square root of 1 minus x squared dx, this is equal to what? That's a harder problem to solve than the numerical equation that I was after. Level 3 is differential equations. For example, f double prime, and I'm going to put in here ordinary, basically single variable differential equations. F prime prime of x is equal to, I don't know, e to the f of x divided by x squared. Good luck, buddy. Find me what is the function that I make two derivatives and is equal to e to that function divided by x squared. And level 4 is partial differential equations. For example, when you combine time and space in the same equation, which is what the heat and the wave equation do. And the list goes on. It gets very, very hard and awful as you go down. Why I'm painting this? Because in this course, and you will see that happening in your regular courses as well, a lot of the time, the professor is going to be guiding you through a problem, and you're going to be playing with something, and you're going to, for example, transform a differential equation into an integral by playing some tricks. Not every differential equation can be, you can do this, but for some you will be able to do that, and the professor is going to be super happy. Aha, and now, see, we have transformed this problem into integration. And they're very happy, and you're sitting there thinking like, I still have no idea how to solve this. Like, what was the game? Why am I even doing this? It's because you were able to go from a more hard level in the dojo to an upper level in the dojo, and that requires celebration. So every time, not every time, but a lot of the time, whenever you can do something to your problem to move from one of the lower levels to one of the upper levels, do it. It's good for you. Everybody will be happy. For example, when you have the wave equation or the heat equation in time and space, one classical thing that people do is separation of variables. We'll look at that later. But when you do separations of variables, you're able to transform a partial differential equation into two couple ordinary differential equations. That's easier to solve. That's better. You can solve that. You have moved from level 4 to level 3. Does that make sense? All right, this is a concept that it was important that you have. Okay, so now, let me check my menu. I'm almost sure that I know what comes. I didn't give you an example. Let me give you some examples, and then we're going to talk about equations in memory. Some examples of differential equations in classical mechanics. You have a body that is moving around in time and space, and there's some forces acting on this thing, and you're trying to describe the trajectory as a function of time of this object, and you write Newton's equations. And Newton's equations tells you all the forces acting on this object is going to be equal to the derivative of the momentum of this particle with respect to time. This is a first order differential equation in the momentum of the particle. Usually we're interested in the position, and if the mass of the particle is constant, this simplifies to m times d at dt of the position vector of the particle. This is a second order ordinary differential equation in the position, given some forces that might depend on time, might depend on x, who knows. Make sense? Differential equation, you solve it, you obtain the trajectory of the particle as a function of time. So this is one example of a differential equation. In quantum mechanics, you have the Schrödinger equation that describes particles. People will argue that you have the time-dependent and the time-independent Schrödinger equation. I am very stubborn. I don't think that makes sense at all. I think you have the Schrödinger equation, and the Schrödinger equation has a time derivative. The time-independent Schrödinger equation is trying to look at the Schrödinger equation from the point of view of normal modes or eigenvectors, which is something that we will cover. So for now, I am going to write the Schrödinger equation, which is the time derivative of your wave function psi is going to be proportional to h, the Hamiltonian acting on your wave function psi. And I always mess this up. I think it's a minus I h bar. Is the h bar there, or is the h bar dividing?
H bar.
Yeah? Anybody remembers? Somehow I feel not. Somehow I feel that the h bar was on this side. So I think it has to be dividing. I'm almost sure. I'm going to put it dividing. So this is, if later it's wrong, doesn't matter. I can correct it. Yeah. I see somebody already typing. Let me know what you see. But I'm almost sure that the h bar is dividing. So this is a differential equation that you have in there. Your Hamiltonian is something that might self-contain derivatives with respect to x. So this is going to be a partial differential equation on your wave function psi, and you have to solve it, and good luck. Make sense? These things describe how the system is going to move. And the examples that I had, I was talking about if you wanted, one of the easiest situations that you can find yourself in where you have to use a differential equation is thinking how the population of bacteria evolve as a function of time. And you write a rule. What is the rule of the game in that case? You say, well, if I have n bacteria at a moment t, after some time scale tau, I'm going to have twice the amount of bacteria. And after the same amount of scale, I'm going to have twice, and that is an exponential growth. If you write down that differential equation, you will see that the solution to that is an exponential. The same thing happens with radioactive decay. It's just that you have an exponential that is decaying, because after certain characteristic time tau, you're going to have half of your sample. That is what is called the half-life of this thing. So far, so good? Okay, there is two differential equations that I'm going to encourage you that you commit to memory, because they're going to come over and over again. The first differential equation that I encourage you to memorize is this one. Let's do it as a function. Let's do it as a function of time. What not? Tell me, what is the solution to this differential equation? E to the, sorry? E to this, to the t. So I hear that the solution to this is e to the t. Am I missing anything from this solution? You can have an amplitude that who knows what it could be. Yeah? Are you with me? I'm going to make it harder for you. Are you ready? And I want, I forgot your name. Daniel?
Yeah.
Okay. Anybody but you, because you already gave me a solution. Now I'm going to complicate this even more. Are you ready? I'm going to put a 3 in here. What is the solution now? Anybody else can answer. It's just Daniel who's banned from answering. Oh. Yeah? Everybody sees it? Very straightforward. Okay. You smart people. Now I'm going to ask some people, what if this is my differential equation? f prime of t is equal to palm tree times f of t. Soon, folks, what is the solution to this? My goodness, I throw you a curveball. Say whatever you think. That's okay if it's not correct.
The tree would be in the exponential with the t.
Makes sense, right? We have talked about this. When I didn't have anything, I just didn't put anything. When I had a 3, I put a 3. Well, if Pablo writes that the differential equation, and I'm going to try not to have to draw this again. There we go. That the differential equation is... I missed some leaves. 1 second. No, that's important. There we go. So the differential equation is f prime is equal to palm tree times f. The solution to that is e to the palm tree, the variable that we were discussing. Period. Don't think. That is, and it's going to come important later. You will see in a second why. But now this is committed to memory. Every time that somebody asks you a differential equation that looks f prime is proportional to f, the solution is e to d, whatever that proportionality was, maybe some amplitude on top of that. Yeah? So now I'm enabling everybody to comment on this. Let's go back to Schrodinger equation then. Isn't Schrodinger equation saying what is the solution to the Schrodinger equation then? So let's do it carefully. E to the what?
Minus I
I over h bar. What else?
T or oh.
No x. I don't see any x.
Oh, then just T.
No t. I'm missing something important. Who is palm tree here? Everything that is multiplying or acting on psi. So what am I missing? No. Where do you see an energy? H. Fantastic. Yes, thank you, Zoom folks. All of these times t, of course. And I need an amplitude. What do I put as an amplitude? Well, things get very complicated because H is a matrix. It's not even a matrix, it's an infinite dimensional matrix because it's a Hamiltonian, which is an operator. So technically, E to the matrix is going to be itself a matrix. So I better act on this, not on a number, but on a vector if I want to recover a vector on the left. So I just put the initial condition, which is my initial wave function at time equals 0. We will talk about quantum mechanics later, but I want to show you the power of realizing that the solution to f prime equals palm tree times f automatically gives you the evolution operator. That you have seen in quantum mechanics. That's why I give you, and if you have not, that's okay. I am here. We're going to talk about quantum mechanics later. But this is something that the first time that I saw it, I was extremely confused and I didn't understand how can somebody come up with the idea that, of course, to evolve my wave function in time, I just do e to the minus I over h bar, the Hamiltonian times time. Well, it comes from here. The second differential equation that I want you to commit to memory is going to look very similar, but it's not. F prime prime of t equals, let's say, minus f of t. Solutions. Sines and cosines, I love it. I'm going to write it sines and cosines. We're going to figure out the details right after writing that, but I want every time that I give you a differential equation that looks like this, the answer to be a quorum, unison, everybody saying sines and cosines. Which sine, which cosine, what amplitude, what frequency. We figure that out later, but it's important that this comes directly like muscle memory. Yep. So the solution to this is some amplitudes, A times cosine of t plus B sine of t, where A and B are two numbers that we can determine by ourselves. Make sense? What if I put a 4? What changes?
4.
Where do I put the 4?
Inside the cosines of psi. Second derivative.
Ah, so Cooper says, wait a minute, I cannot do that. Okay, wait. So Cooper says, I just put a 4 in here, which is kind of what we did for the exponentials. Is this correct? How can you check if this is correct or not? Come on. You can plug it in. So if these were correct, how much is f prime of t? Well, it's going to be 4 times, with a minus, a sine of 4t plus 4b cosine of 4t. And when you make a second derivative, you're going to get that 4 come out again. So you're going to get a 16, which is not the differential equation that I have. So no, this is not the solution. What can I do to solve this?
Multiply.
Sorry?
Like you should put it in front, basically.
Keep trying.
You would put it in.
What if we put a 2? It's going to come out twice. So if I put the square root of the thing that is in there, then I'm good to go. Does that make sense?
Mm.
So whatever I do in here, I don't put directly the number that I saw, but just a square root. And here is a 2. And you can convince yourself, do the math, that this indeed is the answer to this question. What if I have put an ugly number like 35? Well, you just put square root of 35. Make sense? Funny enough, these two things are connected. If you decide to put a plus in here, I encourage you to try. That could have been one of your playgrounds, but I already decided on what your playgrounds are going to be, and it's not that. But if you put a plus instead of a minus, you will end up with imaginary numbers. You will get complex sines and cosines, which are cousins, brothers and sisters of complex exponentials, because exponentials and sines and cosines are the same function. There's many reasons for that. We're going to talk about that when we talk about complex analysis in the 5th or the 6th lecture. Make sense? So these are the two differential equations that you should commit to memory. And we have 10 minutes to actually do the activity. Now, this is the first time that I'm going to try this. I have no idea how this is going to turn out. Be patient with me. We're going to see if it's fun. We have 10 minutes to play the game together. But I do need to rearrange some of these things. Any questions before we do that, friends? Okay. So I need to rearrange things so you can see me. So I need you Zoom folks, you're going to help us as well with calculating things. You're going to be our computers. So I need you to be ready with calculators to estimate things that we're going to do, okay? So these are your 5, 6 places. I hope that I left enough space. I ask each one of you to go from 0 to whenever, how many you are. I'm going to be passing you instructions. So I need somebody to be on 0. I need somebody to be on 1, 2, and 3. Okay, so this is what we're going to do. Let's see if it's, yes. Oh, by the way, I should have asked, do you mind being recorded? Okay, I should have asked that at the very beginning. All right, so here is how this is going to work. If you look behind you, you have an XY coordinate grid, and we're going to solve a differential equation using, well, cheating, using computers from Zoom. But each one of you is going to be passing the numerical value. So the differential equations that we're solving, I'm going to write it here, is f prime, the derivatives of f with respect to x, is equal to 1/2 f of x. Now, if you paid attention to what I was saying for the last 10 minutes, you know the solution to this. But we're going to pretend we don't. With initial condition f of x at 0 equals 1. So the way we're going to work, here you go, you have a chalk, and you have a chalk. You have a chalk, I need the pink chalk, and you have a chalk. And I have stick that you can use to measure. So the way that we're going to solve this you have the easiest work of all. You're going to put this in here. This is 0, so you have to try to more or less, yeah. So you can put that in there. Can you hold it? So you have the easiest work of all. You have this is very hard. You cannot hold both at the same time, but you have the pink lemma of calculation. There you go. So you just need to put the value of the initial value of my function. So the work of all of you is going to be, you're going to have to select in the y-axis what is the number associated with you, with that location in x. What should be for you at 0?
Oh, 1.
1. So put a 1, a blob in there in 1. Like make it as big as possible.
Do I need the ruler for that?
You don't need the ruler for that. The ruler, your friends are going to need the ruler because I will try to help with the ruler. Here, I can grab this one here, so you can put a very nice one in there. Make sense? Okay, so now what we want to do is you want to help to my friend Cooper to know what is going to be his value. How do we find that out?
Plug it into the differential equation.
So if f at 0 is 1, how much is the derivative?
A half.
It's a half. He is 1 unit away from you. So at this moment, you're the one that is computing. He's not computing. Nobody else is able to help. You have the lemma.
Right.
Yeah, so you have the lemma of computing. I don't know if this thing is okay. No, that's okay. I want to make sure that both things captured. So you have to estimate going from the number 1 at 0, how far you need to go to the right. And you can use the sum people if you, this calculation is going to be trivial, I guess. But if the other ones.
To get where?
To where his y value should be.
Okay.
I want to make a curve. Eventually, the objective of this, I want to have a curve in the board. Do you see what you need to do? Some people, you can help her. You're also part of the computing llama process.
Yes. Shared llama.
You see the equation? Can you see the equation? Can you hear us? Looks a bit blurry, though. So
yeah, it's a bit blurry. It's kind of hard to see.
It's a bit blurry. I'm sorry. So the equation is f prime is equal to 1/2 of f. So that tells you the slope. The slope we said is a half.
Right.
So if from that you move 1 unit, by how much will you increase? In y? Half, right? So
So it should be
so 1.5. That
okay.
Give that to Cooper, and Cooper can put that 1/2 in there. Go for it. Okay. Can you use a different color and connect those two with a line? With a straight line as much as you can. Sorry? Yeah. Yeah. Very good. Excellent. Okay, your job is done. You remain there. Now you give the pink llama to Cooper. Now Cooper has to calculate the next step. Okay, so you're at 1 and your value of your function is 1.5. So how much is your derivative? 2/3. You sure? No.
3/2, 3/4, 3/4.
Yes. Yeah.
So we go up.
The some people are not helping you. So that is 0.75. So how much is 3/4 plus 1.5? Some folks, can you help me with that number? 3. So 0.75 plus 1.5. I mean, I know the answer.
2.25.
2.25. Here is a ruler. Now you need the ruler.
Okay.
So make it happen, buddy.
You got to draw your point.
No, you draw the point because
Okay.
yeah. At the end, Troy is not going to do anything. Well, you're going to pass it to the 5th point. Yeah.
Give or take.
So that is 2.25, right? Can you draw me a straight line with the different color connecting the 2 points? We have a perfectionist. Excellent. Very good. Yes. Okay. Very good. So now Daniel has the llama. So what is your value? By the way, if it's easy, write down the numerical value on top of the point so that we don't forget. Otherwise, we're going to be, the next one was 2.25. So how much is your derivative, buddy?
That's going to be
At 2.25.
sorry, 2.25
Uh-huh.
That's my y.
That is your y.
Yes, yeah.
Yeah.
So that's going to be.
That is 1 point something. How much is 225 divided by 2? Some folks with the calculator. We're waiting. The computer is computing.
It's 1.125.
Excellent. 1.12. So let's say 1.1. So how much should be the value that Daniel writes on the third location? And I'm going to move this here.
You have the how much did Daniel do?
3.35, I think so. Okay, make it happen, buddy. Uh-huh. Ah, that's another way of using the ruler. That's very smart. Okay, so make it happen. Oh, beautiful. Can you draw a straight line?
Yeah.
And you already see, I love that you're using the ruler because you're already seeing how the slope is changing. That's okay, that's okay. That's okay. No, you did great. Okay, so now is the turn of Troy. So Troy, what is the value of your function there? Can you write it down or we will forget? And can I ask Daniel and Cooper to move a little bit so we see what Troy is doing? Go ahead. So how do we go from 3 to 4? Uh-huh. Uh-huh. So 1.6 plus 3.25? 3.3, okay, 1.6. Yeah, about, yep. Okay, so make it happen. Excellent, and you know what? That sounds extremely fun, so I want to participate. So I'm going to be the final point. You need help? Okay. Very good. So how much did you say? Around 5, right? Can I have the, yep.
With the llama as well.
Yeah, I want the llama. Hell. So this is 5. I have an easy one. 5 divided by half is 2.5. So I'm going to move a delta x that I need to add that times my derivative, which derivative is 2.5. So I literally move 2.5 extra. So I should move to 7.5, which, no, this time I'm going to use this as I thought, which is going to be, yeah, this is what I originally had in mind. 7.5, which is around here. I'm going to connect these two slope. So you see what is happening in here. The next one, if you were to calculate it, is going to be even further. So now you have an exponential growth. The bigger you are in y, the bigger your rate of change is going to be. That's literally what an exponential is. And you see, this is how I'm going to close the session. I do need to show you your playground. So give me 3 more minutes of your life. You see many interesting behaviors in here. Could I have predicted what my value at 5 was going to be? Just as I heard what Allison was putting in there, could I have known without having to go through this process? Technically, yes, if you know the by hand full solution of the differential equation. That is what means to fully solve the differential equation by pen and paper. Most of the time you can't, because it's a Markov process. It's something where my answer here depends on the previous answer, depends on the previous answer. This is a numerical integrator. We just perform what is called a numerical integrator that integrates the initial condition, integrates. Why integrates? You're adding small changes one after the other. So you're getting the value of the whole out of the chunks of the many different changes that you get. And that's one of the ways that computers solve differential equations. So that is one of the points. The second point, you already can see that if we were to mess up with that initial condition in any way, it's going to propagate and affect the entire solution. That's why most people tell you that a differential equation is nothing without the boundary conditions. you need to tell me where I start, because that is going to change the entire behavior. Make sense? Okay, I'm going to ask everybody to go back to your seats. I'm going to show the last slide, which is the playground for you, and then we are done. Ta-da! That's exactly what you got. Those are the red points that you were calculating for this differential equation. That takes me to the final part. See, yes, you have a question?
Go that high?
Sorry?
We go 12.
Oh,
Ah, I love it. Yeah. So why you didn't go to 12? Very good observation. You screw up. Is an approximate. You start making approximations of approximations, and it carries out. Not only that, there is another hidden approximation that we didn't talk about too much. We were taking steps that were extremely big. The red points that I'm showing you is not the red points that you will calculate by this method. Actually, I didn't realize it. I just put the red points on top of the curve. But if you were to do it by shooting straight lines, this curve is not a straight line. So you will have to take a delta x, a step size that is much smaller to approximate something, but you will always carry out an error that just increases and increases. Make sense? Very good observation. Thank you. And depending on the concavity of the curve, you always will be, and some of them, you will always be below and above. Final thing, playground for next week, together with the playground from Monday. These are your 3 things to think about. The first one is expanding Taylor these functions around x equals 0 up to 5th order. Doesn't hurt that you get some muscle in taking those derivatives and looking at them. Try to visually study how the approximation look when you plot them. Use Python, Mathematica, ask ChatGPT. ChatGPT is your friend. If you don't know how to plot these things, remember as well that I have the videos on how to use Python, and look at the approximations versus the true function. I have an example in here to the right. That is what I'm after. I want you to be able to make this type of plotting where you show the true function and the Taylor series up to some order. In this case, I went up to 5th order. And the final part is an open question. I want you to think, to meditate. Once you find the 5th order Taylor series of sine of x and you compare them between minus pi and pi, is this the best 5th order polynomial that I could have built for sine of x? Is there a polynomial that I can obtain not through the Taylor series, but in some other way? I will teach you how next class. That will give you an approximation that is better. Think about it. Any closing remarks or questions?
no.
With that, we officially conclude this lecture. Sorry for taking 7 more minutes, and I will see you next Monday.
Thank you.
Of course. Thank you soon, friends.
Thank you.
Thanks.
Thank you. Bye.
Bye.